After watching this video lecture, students will be able to calculate problems using the Q equals MC delta T equation. They'll also be able to calculate constant pressure calorimetry problems with appropriate assumptions, and of course calculate bomb calorimeter as well as coffee cup calorimeter problems given appropriate data. We're going to be looking at calorimetry. So basically, guys, calorimetry is the measure of heat flow, and a calorimeter is a device that allows us to actually measure this heat flow. And our typical setup that we have probably used, or each of you have probably used in the past, is a coffee cup calorimeter. We have an insulated system, we have the reaction area, and we have a thermometer to monitor temperature changes. And from this setup, we can determine what kind of changes are occurring for the specific process that we are analyzing. So whether heat is being released or heat is being gained, okay? And so that brings us to our Q values, right? So Q is going to be positive or negative. Now remember, at constant pressure conditions, delta H is going to be equal to Q. Okay, so depending on the type of calorimetry that we're doing, our enthalpy values can be calculated from the analysis of our data set. And we're going to look at this in more detail as we progress. We're going to go ahead and look at the equation and the variables that are necessary in order for us to take our temperature information and our mass information from the calorimeter setup and utilize it to get to our Q value, or our heat value. Okay, and so the equation we're going to use is our Q equals mc times delta T, where Q is the quantity of heat, m is your mass, c is your specific heat capacity, and delta T is your change in temperature. So let's go ahead and let's look at a few of these variables and decide what they mean, and then progress from there. So if we go ahead and we look at the specific heat, C sub S, the specific heat of a substance is the amount of heat, or Q, required to raise the temperature of 1 gram of that substance by 1 degree Celsius. So it's a very specific definition of our heat capacity. Now, we could also define heat capacity in a more generic way, where we're just basing it off a given quantity. So that could be moles or grams or, what have you. But we typically rely on specific heat data for analyzing and utilizing in our Q equals mc delta T equation. And so what we have here is a bunch of data regarding our specific heat capacities of specific substances. I want you to go ahead and notice that the units here are joules per gram times degrees Celsius, which corresponds to our specific definition that we were given for specific heat capacity. And I want you to look at aluminum here and its specific heat capacity versus iron. Okay, so if I have 1 gram of aluminum and 1 gram of iron, it's going to take 0.9 joules of heat energy in order to change that 1 gram of aluminum by 1 degree Celsius, compared to the iron only needing 0.444 joules to exhibit that same change. Okay, so specific heat capacities are going to be specific for both the type of substance and obviously the quantities present. Okay, so how does this connect to our calorimetry? Okay, well remember guys, in calorimetry we have that calorimeter substance or setup. We have a thermometer that allows us to calculate our delta T. If we know what substances are involved in the process, we can find our specific heat, and of course we can always measure our masses before we put it into the calorimeters. Okay, so if we know this data, of course we can plug into Q to get the amount of heat that is being released or absorbed. Now, one more thing I want to point out, delta T here, remember delta T is always final minus initial, so we would take the initial temperature of the solution or of the water in the calorimeter, and then we would take the final temperature, and then we would take final and subtract it from initial to get our delta T. So this is what we're going to be using our Q equals mc delta T equation for in subsequent steps. So if we go ahead and we look at this problem, they want us to tell them how much heat is given off when 869 grams of iron cools from 94 degrees C to 5 degrees C. Okay, so they've given us a bunch of data here, and let's go ahead and write that data set out. Okay, so we have our mass that they provided. They gave us 2 temperature values, which allows us to calculate our delta T, which is going to be negative 89 degrees C. And then our specific heat capacity of iron is something we could look up. Remember we talked about it on the last slide, but that could be tabulated data. Okay, so we have our variables that we need to now plug into this equation. All right, so if we go ahead and we plug that in, we get the following setup, and we get the following answer from our calculators. Okay, and if we go ahead and we look at the units here, grams and grams are going to cancel, Celsius and Celsius cancel, joules is what's left over, which makes sense with respect to what our Q units would be. And then if we check sig figs, we're going to have 2 sig figs, so negative 34,000 joules is what is being released when this iron bar cools. Now remember again, guys, there's no such thing as a negative Q value. The negative sign here for this Q is telling you the directionality with respect to the system of the heat flow. Okay, so 34,000 joules are being released, but there is no such thing as a negative value of the heat energy. So we're going to once again be using our Q equals M times C times delta T, but in this problem, notice that they are asking us to calculate the final temperature of our gold. Okay, so because we are calculating the final temperature of the gold, we're actually going to be first solving for our delta T and then manipulating farther down the line to find our temperature final. Okay, so if we go ahead and manipulate this equation to get delta T all by itself, we end up with, okay, so with the variables that we need are Q, M, and our specific heat capacity of our gold. Okay, so if we go ahead and we write out those variables, we have the following. Okay, guys, please make sure that you are not confusing the units associated with Q and C. Make sure you're plugging them into the right location. Q is always going to have the units of joules or maybe kilojoules, while your specific heat capacity is going to have the joules, grams, and Celsius, or joules, grams, and Kelvin units. So make sure you're paying attention to those and not confusing them. Okay, so if we go ahead and plug these into our equation above, it's going to give us 43.06. Go ahead and do a unit evaluation. We end up with Celsius, degrees Celsius being what's left over. Okay, and we know we're going to be to 3 significant digits here. Okay, so this is our delta T value. Now they didn't ask for delta T, they asked for temperature final. So remember that delta T is equal to temperature final minus temperature initial. Okay, and if we manipulate this, we end up with temperature final being equal to delta T plus temperature initial. So if we go ahead and we plug that in, we're going to end up with the following equation. And that is going to equal 68.1 degrees C as our temperature final. Okay, and that makes sense that our temperature final would be higher because the metal is absorbing heat energy. And basically, this is how you do these types of problems. Okay, so constant pressure calorimetry is something that we're going to be looking at. We're going to be differentiating between that and constant volume calorimetry, which will be discussed later. But for these purposes, constant pressure calorimetry is what it is. It's calorimetry that's carried out at constant pressure. So this is typically carried out on your desktop or your bench top in a coffee cup calorimeter. Again, we've seen the calorimeter before. It has an insulated component, it has a reaction mixture, it has a thermometer that allows us to measure temperature changes. But basically, this apparatus is what is going to allow us to figure out the heat gained or released by a specific process. Now, because the reaction is being carried out under conditions that allow pressure to remain constant, we can take advantage of our enthalpy being equal to our Q of reaction. And we can also use our Q equals MC delta T in order to figure out information about what's changing in the solution, and then use this relationship to decide what's actually happening with the reaction. Okay, so basically if I monitor or indirectly monitor the reaction that's happening here by looking at the changes in the solution, I can use this relationship to then establish the heat associated with the reaction and subsequently the enthalpy of that process. Okay, so basically the calorimeter is going to allow us to have an indirect measurement of our reaction through the analysis of what's happening to our solution. Okay, so they've told us that we have 4.25 gram sample of solid ammonium nitrate that's dissolved into our 60.0 grams of water in a coffee cup calorimeter. The temperature drops from 22 degrees C to 16 degrees C. They want us to calculate the enthalpy change in kilojoules per mole of ammonium nitrate for this process. What we're going to have is we're going to have our coffee cup calorimeter. Basically, we're carrying out constant pressure calorimetry here. And we're going to analyze the temperature changes and the heat changes associated with the solution using Q equals M times C times delta T. Because they have given us the components to figure out the mass of the solution, the specific heat capacity of the solution is going to be assumed to be the same as water. They've told us to make that assumption, and they've told us the delta T of the water. Okay, so if we go ahead and write out those variables, we end up with this set of data. What I want to point out here, guys, is notice for the solution, the mass of the solution, I have taken the mass of both the solid that is being dissolved into the water and the mass of the water to give the total mass of the solution. I've used the specific heat capacity of water. Please memorize this, guys. It will not be given to you all the time. And I've taken and calculated the change in temperature of the solution. Okay, so I can now plug this into the equation above to solve for Q of solution. Now that we have that plugged in, we're going to go ahead and plug in our calculator, and that's going to give us the following value with the units joules. Okay, so that's the Q of our solution. That is the thing that we have directly measured. Now, we're trying to indirectly figure out the Q associated with the reaction. So what's causing the change of the solution? And if we take our relationship of Q of solution equals negative Q of reaction, okay, and we solve for Q of reaction is just going to be the negative of our Q of solution. Okay, so Q of reaction in this case is then going to be 16,000 joules. Okay, so as we see here. So notice it has a positive sign now, simple flip. Okay, so now we've established the heat or the heat released or given off during the reaction process or during the dissolving process. Now they've also asked us to calculate the enthalpy change. Now remember that for constant pressure conditions, delta H is equal to Q of reaction. So in this case, I have my Q of reaction, so delta H is equal to that because this is a constant pressure situation. Okay, and then finally, guys, they want us to express our enthalpy in kilojoules per mole of our ammonium nitrate. Okay, so right now we are in joules for our enthalpy value. Obviously, we're going to move our decimal over a couple spaces, and so our delta H is going to equal 1.61293 kilojoules. Okay, now you can show this or not. As long as you move in the right direction, you're fine. But they want it per mole of ammonium nitrate. Okay, so I need to take my 4.25 grams of ammonium nitrate and convert that into moles. So if I go ahead and plug that in, I end up with 0.05309 moles of our ammonium nitrate. Okay, so I'm then going to take that value for my ammonium nitrate and I'm going to go ahead and divide it into my enthalpy value. So plug that in here. As follows. Okay, and if I plug that into my calculator, I'm going to end up with 30 kilojoules per mole of NH4NO3 as my final answer to the above question. So notice the assumptions we've made here. Of course, guys, we've been told we're using a coffee cup calorimeter. We're assuming constant pressure. We are indirectly getting our Q of reaction from our direct measurement of the data set for our Q of solution. We are also assuming that the mass of the solution is comprised of the thing that dissolves as well as the mass of the water. And they've told us to assume that the solution's specific heat capacity is the same as water. So basically this is how you progress with these problems. Okay, pay attention to units and you should be fine. So we have another calorimetry problem here. In this case, they've told us that we've mixed 50 mils of 1 molar HCl and 50 mils of 1 molar NaOH into a coffee cup calorimeter. When we mix these two solutions, the temperature changes from 21 degrees C to 27.5 degrees C. They want us to calculate the Q of the reaction. They want us to calculate the enthalpy value. And they want us to calculate the enthalpy value per mole of HCl for this specific reaction. Okay, so once again, guys, this is a calorimetry problem. So of course, we are going to be indirectly measuring the interaction between this HCl and NaOH. Okay, so HCl and NaOH, we know that when we put them together, because they're an acid and a base, we know that we get neutralization. So H2O and NaCl are the products that we would produce. And because this is a calorimetry problem, we know we're going to be looking at the Q of the solution directly so that we can indirectly measure our Q of reaction. So our Q of our solution is what we're going to be calculating initially in order to figure out our Q of reaction. Now, there's a few assumptions we're making here, just like we have in other problems. Okay, so first of all, guys, we are assuming that the 50 mils of each of the reactants is going to basically sum to a total volume of 100 milliliters. Okay, so we have 100 milliliters because 50 and 50 give us 100 mils. Now, we are also going to assume that the mass associated with these two solutions is going to basically be having the same density as water. Okay, so the volume of our solution, we're going to assume that its density is the same as water, okay, which is 1 gram for every 1 milliliter. Okay, and so basically what we're assuming is that the density of the solution is the same as the density of water, because these two are basically primarily made up of water, and that's going to allow us to get our mass of our solution. Okay. In that same vein, we're also going to assume that our specific heat capacity of the solution is the same as the specific heat capacity of our water, just like we've assumed in the past. Okay, and that's going to allow us to calculate our Q of our solution. Okay, so we have 100 grams of our solution times our specific heat capacity of our water. Okay, and of course we need our change in temperature, which is calculated by taking our final value of our temperature of our container minus our initial, okay, which is equal to 6.5 degrees C. We'll plug that in, 6.5. Okay, we're going to go ahead and multiply this out. That's going to go ahead and give us 2719.6. Okay, units wise, grams and grams cancel, Celsius and Celsius cancel, joules are what we've obtained. Okay, so that is our Q of our solution. Okay, so now if we want to find our Q of reaction, we're going to go ahead and change the sign of our Q of solution, which is subsequently going to give us the following value. Now, this is our Q of our reaction, so the heat associated with the process of HCl and NaOH interacting with one another. So now we want to find our enthalpy value. And remember, because this is a constant pressure situation, our enthalpy value is equal to our Q of reaction. Okay, so this is our corresponding enthalpy value. The last thing they've asked us to calculate is the enthalpy per mole of HCl for this reaction. They have not specified what units the enthalpy need to be in, so I'm just going to leave them in the joules as they are here. So much like we've done, we first need to figure out our moles of HCl. Okay, so basically if we take our 1.0 molar concentration of HCl, okay, and we multiply it by our volume in liters, the conversion of which looks like this. You know, we have 1,000 milliliters for every 1 liter. Okay, this is going to give us 0.05 moles of HCl. And then now we can find our enthalpy per mole of HCl by taking our enthalpy value and dividing it by our moles of HCl. And that's going to give us the following value. In this calorimetry problem that we have here, we're taking a solid sample and heating it, and then we're going to add that solid sample into a calorimeter containing water. In this context, we are dealing with a solid that's not going to dissolve in solution, so we do not sum the total masses of the sample that's added to the water that's in the calorimeter. Okay, so in this situation, the Q of our solution is going to actually be Q of our water, because we're actually measuring the mass of the water directly, the temperature of the water directly, and that's going to allow us to figure out the Q of the reaction, or in this case, the Q of the solid. Okay, so this is the relationship that we're going to use, and basically the approach that we're going to take is to find the variables of the known, which is the water, to help us find an unknown value, which is the specific heat capacity of the solid. So we're going to calculate the Q of our H2O, okay, and we're going to plug in the mass of our water, okay, times the specific heat capacity of our water, times the change in temperature of our water, which goes from 25 degrees C, 25.10 degrees C to 28.49. So that's our final temperature minus our initial. Okay, and this is going to allow us to figure out the Q of H2O, which is equal to 709.188. Okay, and unit evaluation is going to leave us with joules. So this is the Q value associated with H2O. So this is what we've measured directly. Now this is going to allow us to figure out the Q of the solid indirectly by using the relationship we see here. Okay, so Q of solid is going to be equal to the Q of the H2O, but just with the opposite sign. So this is our Q of our solid. Now, they don't want the Q of the solid. What they want is the specific heat capacity. So they want the C variable. So Q of our solid is equal to the mass of our solid times the specific heat capacity of our solid times the change in temperature of our solid. So the variables that I'm able to determine, obviously I know Q. They've provided us with our mass. Okay, and delta T can be calculated from the information provided above. So the Q of our solid is provided here. Okay, the mass of our solid is 25.64 grams, as it says in the problem above. Okay, our C of our solid is what we don't know, and we're trying to figure out. Okay, and our change in temperature of our solid can be calculated from the information provided. Okay, so we know that the initial temperature of our solid is 100 degrees C. Okay, and we know that the final temperature of the solid is the same as the final temperature of the water inside the calorimeter, so 28.49. So final 28.49 minus 100 degrees C gives us negative 71.51 degrees C as our change in temperature for our solid. Now, if we go ahead and we manipulate the equation here, we can get C solid all by itself. So our specific heat capacity of our solid is going to equal the Q of our solid divided by the mass of the solid times the delta T of the solid. Okay, and we can go ahead and plug in our variables. Okay, so C of our solid is going to equal negative 709.18 joules divided by the mass of our solid, which is 25.64 grams, times negative 71.51 degrees Celsius. Okay, and we go ahead and plug those into our calculator. That's going to give us a specific heat capacity of 0.387 joules per gram degrees Celsius. Okay, and that's the specific heat of the solid that we used in this calorimetry problem. So in constant volume calorimetry, basically what you have is known as a bomb calorimeter. Bomb calorimeters are a much more intricate setup. And basically what ends up happening is you have an enclosed sealed container. And so There is actually going to, be variable pressure in the situation. And so we're not going to actually be able to use this enthalpy being equal to Q of reaction, straight away without some additional assumptions. However, guys, I do want to point out that a lot of times we do kind of just basically use the approximation between these two, because although it will be different, it's pretty close. Now, technically speaking, the change in internal energy is going to be equal to the Q of reaction process when carried out in the constant pressure calorimeters, or the bomb calorimeters. However, this approximation is usually acceptable when we're expressing things in this class. Okay, now the equation that we're going to be using to calculate Q of reaction is basically we're going to take our specific heat capacity of our calorimeter, notice this negative sign, make sure you don't forget it, times our delta T. So there's no flipping and flopping of things or changing signs. Basically, you will have the calorimeter's specific heat capacity. You plug that in and the corresponding delta T value, and you will get the Q of reaction from this process. Okay, so let's go ahead and let's look at this example. 500 grams of fuel, 500 gram fuel samples burned in a constant volume bomb calorimeter. Okay, so they've told you that you're using the constant bomb calorimeter, so you know that you're going to be utilizing this type of equation. This bomb calorimeter has a heat capacity as follows, and the temperature of the bomb calorimeter when we burn these 5 grams of fuel is 3.25 degrees C. So they could have asked this in several different ways. They could have totally left out constant volume bomb calorimeter, and they could have said, 5 gram fuel sample is burned in a calorimeter that has a heat capacity of this. Okay, so notice the units here are different for our heat capacity, and notice they would have told you that the calorimeter has this heat capacity. Remember that this C value here is for the calorimeter, so for the instruments that's being used to run this reaction. So even if they don't tell you it's a constant volume or a bomb calorimeter, you can get the hint based on the units associated with the calorimeter, them telling you that the specific heat capacity of the calorimeter is as such, etc. All right, so now that we kind of understand that, let's go ahead and let's look at what they want us to actually figure out. So they want us to calculate the heat given off by the sample in kilojoules per gram. Okay, so our heat of our reaction is going to be calculated in a very similar way that we've been doing. We're just going to plug in our specific heat capacity and our change in temperature, which we've been given both of those. We multiply those out. It gives us this answer, so negative 8,160 joules, right? Celsius and Celsius cancels. Okay, those units cancel, so joules are what's left over. Now they want us to calculate the heat given off in kilojoules per gram. So obviously we're going to take our joules and convert them into kilojoules. So pretty straightforward there. Okay, now they're then wanting us to calculate the heat given off for this reaction. So this is a heat of combustion because we've combusted a fuel. But they want us to calculate this based on kilojoules and grams. So we know that our Q value is equal to, should be negative 8.16 kilojoules. Okay, and we're going to divide out by our mass, which is 5.00 grams. Okay, and that will give us this answer here. Okay, so our heat of combustion, when we combust this sample, when we burn this sample, we get negative 1.63 kilojoules for every gram that is burned. So the bomb calorimetry calculations are really nice because you don't really have to pay attention to all the little details like you do with the constant volume calorimetry or constant pressure calorimetry. But, obviously you're still going to be looking at units, you're still going to be looking at what the sample is, etc. So just make sure you're paying attention to what type of calorimetry based on the units that you have or based on how the question is actually worded. And if you follow those steps, you'll be fine.